I'm Ryan Wigline, and this is my ENME 489 final project. For this project, we had to scan an object on campus with our LiDAR, and we're doing this to see how LiDARs interact with everyday objects and how the different coefficients can be affected by the object that we are scanning. For this project, I chose to scan the Testudo statue, and I chose this because Testudo is obviously the mascot of the University of Maryland, and it's a recognizable symbol on campus. And here's the location of the Testudo statue. It's by Riggs Alumni Center. My LiDAR setup. By moving the LiDAR up and down and using known geometries, we can get the angles and get the distances between the laser and the target. Here's my LiDAR mount, and it's attached to a tripod. And I have the wires connected to my computer for like the VNC connection. I got two batteries, each for the Raspberry Pi and the Arduino. And then I have the laser holder here that will hold the line laser. And I have the camera mount here too that's attached to the Raspberry Pi. And so the laser acts as a transmitter, and the camera for the Raspberry Pi will act as the receiver for the reflections from the wall of the laser light. And then all the processing, it should go to the Arduino. Then later I'm transferring the Arduino, not the Arduino, the Raspberry Pi. For this project, we're using LiDAR, and LiDAR is an example of remote sensing. And another example would include something like radar. And remote sensing is just the method where the thing being collected is not in physical contact with the instrument to take measurements. This LiDAR would be an example of an active LiDAR sensor. Active is when the LiDAR sensor itself has to emit the radiation, the laser beam, in order to collect data. And then passive would be when the natural light that's given off, and the camera would see the natural light for the data collection. LiDAR is the one we use light and bounce light off objects to get a sense of what the objects look like. And we can see this in this diagram given to us by Dr. Mitchell, a basic flowchart of what a LiDAR looks like. And so we can see that there's radiation that's emitted, in our case our laser pointer, and it bounces off an object and gets picked up by a receiver. So knowing that C delta T over 2 is going to be the range of the light, we can slowly build up the different ranges, which will give us a picture of what the object looks like. My LiDAR does not use this technique. My LiDAR uses distance between the color using OpenCV of the red line and the pixels from the center to determine the distance, and using our known geometry of the LiDAR itself to find this range to give us the picture of the object. As we can see in this example, which was done during the semester, the green light on the stoplight is being tracked by OpenCV programming. My LiDAR uses the same principle as finding the color of the red laser and finding the distance between the center of the camera and the distance to the center of the camera. Here we can see the single point laser setup that I had for initial testing, and we can see the results of this calibration. The calibration is awful, it's horrendous. It doesn't look good whatsoever. So when we actually did the line laser using the setup here, we can see the results are actually a lot better. And we see about the sweet spots around 60 inches, which is where the theoretical data meets the experimental data, which means that it should have the best results at this single point. So the next step was to go out and start mapping Testudo, but I ran into an issue. The issue was that the base and the statue itself had very little returns coming to the camera. So this is what we get from the pictures. When we see both pictures, we can't see any red laser whatsoever. And after repeated attempts at filtering and using saturation code, we still get no returns whatsoever. So then we have to think back to the LiDAR equation, and one of the components of the LiDAR equation is the scattering coefficient. So we're going to increase the scattering coefficient here, and the way we're going to do this for the statue itself is to add flour all over to Testudo. And we do this by covering him in every orifice we can get to. So here's Testudo after I covered him in flour. He's all dusty. I tried to get the best I could. And yeah. See the line down here where I tried to get laser points. I wasn't getting anything. I'm out here mapping Testudo, and I've already begun. And so I wasn't really getting any returns off Testudo's top surface, so I had to put a bunch of flour on it. So you can see here, I just put, see, 5, 5 already begun, 5. And so we enter here, press 3, 5. Oops. 3, 5, 5. Enter. So we can get some returns. It's kind of light, but we're still getting something. We can filter out later. Let's go hit another one. So hopefully we can see it turns off here in this feet. That's what we're hoping for. So let's go to the next one, hit 3, 6. 6. Yeah. Here, hit 3, 5, 4. It's negative. Into that. So change the picture here. You see it turns again, so we're going to accept that one. We're going to keep repeating the process until we have at least 20, hopefully more data points. So after coloring Testudo and Flower, we can see that we do get a bunch more returns. You can also see that in person the laser appears brighter. After covering the Testudo statue and Flower, I also tried covering the base in Flower too, but I got no returns. So this made me come up with a different solution, and this new solution was to cover the base in the shower curtain. Now that we can see, the shower curtain does get far more returns than it would without the shower curtain. We're filming it for the base. I'm just continuing setting up, set 25. 55. Look at it. All good. You can see. You start to see some of the wrinkles in the shower curtain. You can get some fits, but we'll just go ahead and accept it. So here we can see the different views of the scans I will be taking. There's 6 views in total, which would give us 10 scans. And we can see here there's one in each face, and then there's 2 front orthogonal views, which will help give a better resolution to the front of Testudo. So we'll use these views to start to stitch together Testudo. So after getting all my scans of Testudo, I opened PyCharm to use Python, and I have here the data generation.py file that Dr. Mitchell gave us. And so here I have my lower and upper bounds for my HSV filter, and I also have the files here. The ones not being used are commented out, so you can see here I should have 10 files specified for each of the faces, and the 2 orthogonal, and each of the face has the base and the Testudo statue itself. So I just went in here and I have down here, I have like side 1 and front. So I have here the commands that write the points to the text file, and then you can see here that I just have for like side 2, I have to reorient it, stuff like the offsets to get it to match with the front face, and the front face was the reference for all my files. And we see here we have like back, and for the back we have to flip X and Y and add offsets, and for orthogonal here we have to apply rotation matrix so that we can get it to align with the front face. And then we slowly just build up the files together, and then we add the bases at the end of adding the Testudo statue itself, and slowly we add up and get the Testudo file. And we can also hear that for the front face, front statue, I did a rotation matrix, as well as the back base I added rotation matrix because they weren't exactly aligned when I took the images. We can see here me compiling the scans together. This is just me going through Python through iterations, adding one scan after another, and combining it to get the right offsets and everything. And we see here it comes together pretty nicely, and then it's starting to look like Testudo. As more I add the scans, all my individual 3D point clouds together, we get this as the final 3D point cloud of Testudo. So we can see common identifying features such as the shell Testudo. We can see the head. We can see the head has some curvature. He's looking to the left, not looking straight ahead, which is where it's supposed to be. We can see stuff here such as the arm a little bit on the on his right arm. We can also see his left arm too. It's very dense here. We can see it ever so slightly. and the head also looks like it has correct thickness. I'm going to show you here, if you look closely, there's an M, which is, we can see in the front of the testudo. And I actually had to take the front without the M, and I decided to add the front lines to it, covering over the M, because if we didn't add these, the base wouldn't be as flat. And when I tried it multiple times, and getting rid of these lines doesn't actually let the M appear in the mesh. So I decided it wasn't worth it. We can see other features such as the base. It's pretty square or rectangular, and we can see the back of the head. This, I think, is a great view of Testudo. So I went out and used a tape measure to get each of Testudo's measurements, and we can see here comparing it to the actual scan I got using just the point distances in MATLAB. Like you can see they're all pretty reasonable. For example, the length calculation is at less than 4% error difference, so I think that's still pretty reasonable. First, first we're going to do show normal. Then we're going to do compute normal to point set. We're actually going to have to do a pretty high number like 7,500. And we're going to do the trackball center, make the trackball center 0. And apply that. This will take quite a while. After applying the normals, we can see that the back half test here actually looks pretty good with the normals, then the front half looks horrendous. So we're just going to go to filters, meshing, and then do a Poisson surface. Take all this. We're going to get this, which is pretty normal. But then all you have to do is you just look inside and you can actually see Testudo's head there. So just going to clean it up. Delete a bunch of these surfaces here and try to clean up the back and try to make it a flat surface down here. It kind of bulges. And then try to... So after cleaning up the big bulb we had before, I cut away a bunch of the pieces and cut off some of the base. But we can see here how the general map of Testudo 3D point map matches the mesh that was created by MeshLab. So next we'll put that into Creo and make a base so that we can actually 3D print the part. So I imported Testudo into Creo and got this 3D part. And so I added a base Testudo and I also tried to engrave Testudo's name to the base. We'll see how that turns out. So the next part would be to send this to TechnoWorks and get them to 3D print it. And we'll see how it turns out. And lastly, here's the 3D printed Testudo that I made using my scans.